78% of the air we breathe is nitrogen. It is a colorless, odorless gas that forms the very envelope of our atmosphere. At the other extreme is bismuth. It is a heavy, dense metal, famous for these brittle, iridescent crystals. Despite these physical contradictions, nitrogen and bismuth are members of the same chemical family, group 15. Phosphorus, arsenic, and antimony fill the space between them, completing a perfect material spectrum that spans from a light gas to a heavy solid metal. This physical variance follows a predictable phase transition governed by a single subatomic rule. Beneath these macroscopic states lies the shared quantum architecture that unites the group. Every element in group 15 possesses exactly 5 electrons in its outermost valence shell. This specific architecture is the ns²np³ configuration, the fundamental rule for the entire group. Because atoms are most stable with an 8-electron octet, this 5-electron shell creates a specific 3-electron deficit. This deficit drives the elements to fill their shell by either sharing electrons in covalent bonds or gaining 3 extra electrons to form -3 anions. If the electron count is the constant, the physical transition down the column must be driven by a single changing variable. We can visualize the group as a vertical stack, starting with nitrogen at the top. Moving down one position requires adding a new principal electron shell. This causes the atomic radius to swell. As we move down to bismuth, the atom physically expands. In bismuth, those 5 valence electrons are now separated from the nucleus by multiple layers of dense inner shells. This expansion pushes the crucial valence electrons further on. Bismuth's massive radius means that tether is stretched thin. Inner shells act as a physical shield, weakening the grip. This grip is quantified as ionization energy, the force required to pull an electron away from the atom. This graph shows ionization energy plummeting as radius increases. The larger the atom, the easier it is to remove an electron. A second line for electronegativity shows a similar decay. The larger the atom, the less power it has to attract shared electrons. This swelling radius effectively neutralizes the atom's grip on its valence electrons, forcing a shift in how these elements behave as matter. We can map these subatomic trends directly onto the material properties we see in the lab. In this blue zone, the high electronegativity of nitrogen and phosphorus locks electrons into rigid covalent bonds. This rigid electron lock is the hallmark of nonmetals, resulting in stable gases and reactive solids. In the purple zone, arsenic and antimony hold an intermediate grip on their electrons. These are the metalloids, possessing a hybrid of metallic and nonmetallic properties. Finally, we reach bismuth in the red zone. Bismuth's massive radius and weak electrostatic tether allow its outer electrons to detach and flow freely. This free flow of electrons defines metallic character. It is simply the result of an atom becoming too large to hold its own outer shell. These subatomic dynamics determine the roles these elements play in our world. Nitrogen's triple bond is exceptionally strong, resulting in a chemically inert gas. In our atmosphere, this inert nitrogen acts as a crucial diluent for oxygen. Without it, the atmosphere would support rapid and uncontrolled combustion. The ability of nitrogen and phosphorus to form these rigid, predictable bonds makes them the structural foundation for DNA and ATP. Because life depends on these specific bonds for growth, we harvest nitrogen and phosphorus on a massive industrial scale for agricultural fertilizers. Phosphorus also leverages its reactive non-metal nature in consumer products like matches and fireworks. The sudden break of these phosphorus bonds provides the energy release for these explosive displays. The high electronegativity of the top elements is what fuels both biological construction and chemical energy. Further down the group, we find uses for elements with a weaker grip. The intermediate electron grip of arsenic and antimony makes them ideal for the manufacturing of modern semiconductors. In medicine, the specific way these metalloid compounds bind to proteins allows them to interfere with cellular pathways, providing a targeted treatment for acute promyelocytic leukemia. Looking at the entire group, we see the complete transition from an atmospheric gas to a heavy metal. The behavior of group 15 demonstrates how the periodic table functions as a predictive physical narrative. Starting from the subatomic constraint of the ns²np³ configuration, we can logically deduce the macroscopic behavior of matter.